Okay, we're going to solve number 21 from the homework by way of an example, and we're going to do it two ways. We're going to first do what I like to call the brute force method, and what that means is we're not going to apply the Heaviside function initially in order to put the piecewise defined R value together. Instead, we're going to treat it as two separate problems. Now, clearly, there's times when you don't want to do this. If each one of these functions is complex, it sometimes means almost doubling your work. In this case, it's not, because the second function, when t is greater than pi, is 0. So let's take a look at the equation, and let's talk about the way we're going to solve it first. Y double prime plus 9y equals the piecewise defined 8 sine t when t is less than pi, and 0 when t is greater than pi. The initial conditions are y naught 0, and y prime naught is 4. Well, what I want to do first, and I'll do this off to the side, is do the piecewise defined Laplace transform of the R values, because we know we're going to plug it into our algebraic expression. So this is what it'll be. 8 sine t, the Laplace transform of that is 8 over s squared plus 1, and that's when t is less than pi. And when t is greater than pi, the Laplace transform of 0 is just 0. Okay, so let's recall that y equals s plus a times y naught plus y prime naught plus r multiplied by q, which is s squared plus as plus b in the denominator. Remember that we derived this yesterday by looking at the general second order equation and applying the Laplace transform method to it, all right? What we want to do now is write down what y would be when t is less than pi. And of course that means we're going to plug in the top r, not the bottom r. Okay, so let's plug everything in. Y will equal s plus a is 0, so it's s plus a times y naught, which is 0. So that whole thing gives 0. Y prime is 4 plus r, which is 8 over s squared plus 1, and the whole thing's over the denominator, which is s squared plus 9. Well, to make this less of a complex rational expression, I'll put 4 over the same denominator, so it's going to be 4s squared plus 4 plus 8, that's plus 12, and that's all over s squared plus 1 times s squared plus 9. I don't want to get bogged down in partial fraction decomposition, so I've already done this decomposition, and it ends up giving you 1 over s squared plus 1 plus 3 over s squared plus 9. And these are easily recognizable Laplace transforms of sine functions, so when it's time to write yt, I just do the inverse Laplace transform of the algebraic expression, and that gives me sine of t for this, and sine of 3t for this. The only problem is this solution is limited. This is only when t is less than pi, because that's the value of r that I used in order to actually find the algebraic expression and then turn it into this. So we have to do the whole thing again. We have to go back to this line right here and say, hey, suppose t is now greater than pi. Well, then now my new y, same as the old y, except now the new r is 0. And that simplifies things a lot. It's just 4 over s squared plus 9, because the old r value goes away, and that's what made this hard to begin with. Well, this guy is almost a sine of 3t again. It just needs a coefficient, because this has to be a 3 on top, so it's 4/3 of 3 over s squared plus 9, and now it's a perfect sine of 3t. So the y for this one would be equal to 4/3 of sine of 3t. And remember, this one's limited to, this is t greater than pi. So how can I still put it together into a single expression? Well, I can still do that, because remember, we can build a function that changes definition at a value from one set to another by using the Heaviside function. So let's do that. I want an overall y for all t, not just t before or after pi. So to do that, I'll begin with what the first function is going to be. Up to pi, it's going to look like this. So sine of t plus sine of 3t. And this is when things are going to start to change. At pi, I want it to switch to have a coefficient of 4/3 on the sine of 3t. So I need to add 1/3 sine of 3t plus 1/3 sine of 3t. And I need to make the sine t go away because it doesn't exist after t equals pi. So minus sine of t. And then, of course, I have to take this whole part of the function and multiply it by the Heaviside at pi. So what this is going to do is have a value of 0 from 0 to pi. So it makes all this go to 0. So it doesn't impact the first half of the function up to t equals pi. It'll just deliver this, which is just what we wanted. And then all of a sudden, when t is pi and above, it's going to activate this part of the function because the Heaviside function turns into 1. So it'll be 1 times this instead of 0. And it'll be an extra 1/3 sine 3t. That'll make this 4/3 sine 3t, just like we wanted. And it'll be negative sine t, so it'll actually cancel out any contribution that gives. So this is it. This will be the one function that solves the entire differential equation at these initial conditions. And you can see I didn't have to apply the Heaviside function at the beginning. I could sort of brute force my way through and solve the problem twice and then build the solution out of what I knew the two solutions would look like, right? This is one way to go. And on tonight's homework, feel free to work it this way for all of the problems. There's nothing inappropriate about it. However, there's a more powerful and elegant method that at times takes more time. That's why I wanted to show you this, because this is a preferred method when one or the other of the R piecewise defined are relatively simple. I think this is the way to go. But if they're both relatively complex, instead of doing twice the work, you can just do one complex problem instead of two of them. Okay, in the next video, I'll show you how we're going to solve 21, except we're going to resolve this into a single continuous function. Well, not continuous, but at least a single Heaviside function before we even start the process.